right, so in Algebra 2, you guys found solutions involving complex numbers, and we did this by factoring and then using quadratic formula and so on. Okay, so we're going to do a little recap of that. So if we have a complex number and we're trying to find its solutions, we're going to find the solutions of all kinds of complex numbers in pre-calc, okay? But we did some similar stuff in Algebra 2 when we had things like x to the fourth minus 1 is equal to 0. So if you factor into x squared plus 1 times x squared minus 1, and you set it equal to 0, the x squared minus 1 continues to factor into x plus 1 and x minus 1, and the x squared plus 1 does not, right? It stays how it is. We know from Algebra 2 that if I have an x to the fourth, I should have 4 solutions. Now, those solutions could be like repeated, like I could have 1, 1, and -1, -1, right? That's not the case in this case, though. There's actually 4 separate solutions. All right, so when I set my x squared plus 1 equal to 0, I get x squared equals -1, so I get x equals plus or minus I. And then this is going to give me x equals -1 and x equals 1. So we have 4 solutions. So we have 1, -1, I, and -I. If we decided to graph those on the complex plane, the real and imaginary axis, do you guys see where they would be located? I'd have 1, I'd have I, I'd have -I, and I'd have wait, I did that wrong. 1, this is I, this is -1, and this is -I. I said them in the wrong order. Notice how they're all evenly spaced, 90 degrees between them, right? That's all of our answers. Okay, it actually turns out that if I have, x to the 8th minus 1 is equal to 0, those are all evenly spaced as well. And there's 8 solutions. And those 8 solutions then would be, if I do 360 divided by 8, they'd all be 45 degrees apart. So x to the 8th would have all these solutions, but you'd also have solutions in here going around the circle. Okay, does that make sense? So they would be things that would look like root 2 over 2 plus root 2 over 2, I. Right? It's kind of crazy. All right, so let's look at this one. So x to the 6 minus 1. So if I have x to the 6 minus 1 is equal to 0, we actually solved this last year. And you guys hated every second of it. And you're probably going to hate it again, but I don't care. We're going to do it anyway. So if I have x to the 6 minus 1, we're going to factor first with the difference of 2 squares. So we're going to say, oh, well, that's just going to be x cubed plus 1 multiplied by x cubed minus 1. Okay. Now we see that we have the difference of 2 cubes, or well, the difference of a cube and the sum of a cube, right? So now I'm going to take that x cubed plus 1, I'm going to factor it. Do you guys remember how to do that? Binomial and trinomial? So small parenthesis, long parenthesis. We're going to drop the cubes, x plus 1. Square the first item, so this item here, if I square it, I get x squared. Square the last item, so this number here, if I square it, I get 1. That goes on the end. What goes in the middle? Yeah, the x times 1, the two things multiply together. So I'm going to have x. And my signs spells out a word. Soap. Same, opposite, always positive. So same, opposite, what we had, always positive. Okay, so that's for this first one here. That's what all of this was. Okay, now we're going to do the other part. So let's do this part. Okay, again, binomial, trinomial. We drop the cubes, x minus 1. Square the first item, square the last item, multiply the two things together. We get 1x in the middle. Don't worry about the signs until the very end. Same, opposite, always positive. That's how that one factors. So right now I know 2 solutions. I know that my first solution is -1, my second solution is 1. Okay, but I should have how many total? 6 solutions. So how am I possibly going to find solutions from these? The quadratic formula, that's right. So we're going to do a quadratic formula for both. So I'm going to say x equals -b, so -1 is 1, plus or minus the square root of 1 squared, or well, -1 squared is 1, minus 4ac all over 2a. So I get 1 plus or minus I root 3 all over 2. Do you guys see how I got I root 3? Because I had 1 minus 4 in there, which is the square root of negative 3. So when we have a square root of negative, we have an I. So we have I and then the root 3, which looks like 1/2 plus or minus root 3 over 2 I. Okay, so kind of let's go over here to this graphing area. And let's think about where one of those is located. So if I have 1/2 for the real part, that means I go over to 1/2, and I go up to root 3 over 2. So it's up here. Okay, what about the other one? 1/2 minus root 3 over 2. That goes down here. Right, does this make sense? If I actually had the unit circle drawn in, these would be unit circle values. Let me draw on the unit circle. So I would be right here, and I'd be right here. Right, does that make sense why their unit circle value is 1/2 comma root 3 over 2? All right, we also have 1 and we have negative 1. So here's 4 of our solutions graphed right now. Okay, what about the other 2? Let's see. So I'm going to do x equals negative b, so negative 1, plus or minus the square root of b squared is 1 minus 4ac all over 2a. So this one ends up being negative 1 over 2 plus or minus. You guys see how we have the 3i again? Square root of 3i. So square root of 3 over 2i. And those end up being symmetric over here. Okay, so I told you there's something that's really cool that really makes, you know, like I love art. And so this is like, it really pleases me to see something like this. So beautiful. Math is beautiful, right? Look at this. If I take 360 degrees and I divide by 6, right? Because I want 6 solutions. How many degrees separate them? 60. Look, 60 degrees, 60 degrees, 60 degrees, 60 degrees, 60 degrees, 60 degrees. They're all equally spaced. Mine doesn't quite look equally spaced. So I could just jump straight to the solutions by saying, oh, I'm going to start with 1, and then I'm going to go 60 degrees off that and get the next one. Then I'm going to go 60 degrees off that and get the next one. Does that make sense? I can get these right away without even doing any of this quadratic formula business. Okay, so it's kind of cool. These are called roots of unity. The word unity just means 1, like the unit circle, right? So each solution above is called the 6th root of 1 or 6th roots of unity. Therefore, each solution to the equation z to the n equals a plus bi is called the nth root of a plus bi. So in the real number system, we know that x to the 4th equals 16 actually only has 2 solutions, 2 and negative 2, if I have to have real solutions. But in the complex number solution, it has 2, negative 2, 2i, and negative 2i. And that happens because we know that I squared is equal to negative 1 and I to the 4th is equal to 1. Okay, so back when I first started teaching pre-calc, I mean, I feel bad for the students that I had in my first couple years teaching because it was rough. And I made them do all of this just based on this formula, and I never like realized, oh, they're all just equally spaced around this thing. And I made it really hard for my students, and that was mean of me. All right, I've become a better teacher. The older I get, the better I get. So we're not going to memorize this formula. I'll give it to you. You can have this formula if you want it. But look how crazy that formula is. Isn't that mean of me? I should never have done that. All right, all we need to do is we need to find one solution. And once you get one solution, everything's going to be evenly spaced around there. Okay, so let's look at this. So it says find the third roots of z equals that. Ooh. All right, so if I'm finding the third roots, think about how I found z cubed yesterday. We just did this yesterday, right? When I found z cubed, what did I do to this? You don't have to write this, just look up here. I cubed it. What did I do to these? I multiplied by 3, so I'd have like 360 plus I sine of 360. Okay, this is still de Moivre's theorem. De Moivre's theorem, right? It's still the same. We're just going backwards. We're taking like a root of it, okay? And when we take roots, we know that we have more than one solution. Okay, so instead of doing cubed, what am I going to do? I'm going to take the cube root, right? So I'm going to have the cube root of 8. And then I'm going to do cosine of 120 instead of doing times 3. 120 over 3. You got it. So I get this. Okay. But I wrote cube root of z. This isn't the only cube root of z. There's 3 answers. So instead of writing this, I'm going to write z1 is equal to. That's the first one. And then I'm going to find Z2 and I'm going to find Z3. I'm going to find all three. It's not bad, I promise. I'll hold your hand through this whole process. All right. So what's the cube root of 8? 2. So I'm going to have cosine of 40 plus I sine of 40. You can write your cis thing if you want to. So if you want to write it as 2 cis 40. Done. That's the first answer. Okay, now I told you they're all evenly spaced. It's beautiful. Beautiful math. If they're all evenly spaced, and we have 3 solutions, I'm going to take my 360 divided by 3, and I'm going to say, these are all 120 degrees apart. This is the space between them. So what's the next one going to be? Yeah, I'm going to have 2 cis 160. And then the last one, 2 cis, add another 120. 280. Those are our 3 solutions. Could I find those as decimals and so on? Yes, I could. I could find those as decimal answers. Are those unit circle values, though? Like 160, 280? Not really. Like, I'm not going to find those as root answers. All right, Brooke, you with me? All right, so next up, so fifth roots. So now I'm going to have 5 solutions. Woo, 5 solutions, whoa. So I'm going to take that 360 and I'm going to divide by 5. When I do, I know that there's 72 degrees between each one. So I got to find this first one. Okay, this one's different than the last thing, right? The last one was already in trigonometric form for us. It made it so easy for us. So Hallie's like, oh. All right, we got to put this in trig form first, which is what you guys did a couple days ago, like on your homework. That was the easiest homework ever, you guys remember? It wasn't that bad. So we're going to go, unless you messed up your angles, which some of you guys did. And you're fixing them, right? So we go negative, and then we go negative. Notice how I'm going the same amount, negative and the negative. So what's this angle then? 45 past 180. So our angle is going to be 225, right? My r is going to be the square root of whatever, I don't need the negatives in there, but negative 16 root 2 squared plus negative 16 root 2 squared. So you guys end up getting 32. You know how I knew that right away? Because I teach geometry. And I know that if I have 16 root 2 and I have 16 root 2, and we just said that this was a 45-degree angle, how do I get to this? I multiply by root 2. Yeah, it's a special right triangle. Yeah, so I think you guys are like, how did she do that in her head? All right, so I get r is equal to 32. Good. That's a good one to remember from geometry. If you're going to remember anything, remember 30, 60, 90 triangles. All right, so if I want the fifth root, so let's say we're finding the first one. Well, first let's write our z in that other form. So z is going to be 32 cosine plus I sine of 225. So if I'm finding the first one, I take the fifth root of 32. Then I have cosine plus I sine of 225 divided by 5. So I'm going to get 2 cosine plus I sine of what? Help me out. 225 divided by 5. 45. All right, that's the first one. Now I'm just going to list these out. Z2, Z3, Z4, Z5, and we're going to get them right away. Because the beauty of mathematics. So we have 2 cosine of, well, I'll write cis, cosine plus I sine of 45 plus 72, 117. Thank you. Keep adding 45. Give me my other ones. 1. Oh, 72. What did I say? I said 45? Oh, okay. 117. So add 72. What do we get? 189. Add 72. 261. Add 72. 3 what? 33. Those are our answers. Done. Kind of cool, right? So you can, instead of doing all this factoring, I mean, think about if it was z to the 5th. Like solving something that's like x to the 5th would be really hard to do. Like, how do you find all those answers? We just did. All right, so 3. So find the 4 solutions to the equation. So maybe it's set up like this where it looks like an equation. That's all right, we got this. It's just saying x to the 4th is equal to, and we're going to add this to the other side. So we're going to say 81 over 2 plus 81 root 3 over 2i. Okay? So we're asking for the 4th root of that complex number. Make sense? So let's write this complex number as z. So our complex number, z, is going to have our radius, like that modulus, and the theta, right? So we need to find those. Sometimes you can kind of think about where they are. Do you guys see how these numbers look really similar? One of them just has a root 3 attached to it, right? So if you were sketching it out, it's in the first quadrant. We go out a certain amount and we go up a certain amount. This one's whatever that number was times root 3. Any guesses on what our degree is? Yeah, it's 60 degrees. Okay, if you didn't know that, then we go through and we do our tangent of theta is equal to 81 root 3 over 2 divided by 81 over 2, and it gets a little messy for a sec. And then we do inverse tangent and we get 60. So on your calculator you can do inverse tangent and you'll get 60. Just be careful, there's like lots of parentheses going on there, right? I'd probably find the decimal version first and then do inverse tangent of the answer. All right, and then our r. So remember how we were just talking about 30, 60, 90 triangles? If I have my number and I have my number multiplied by root 3, this is going to be my number multiplied by 2. So I'm going to have 81 over 2 multiplied by 2. It's going to be 81. But again, if you didn't know that and you didn't recognize the 30, 60, 90 thing, you would go through and you'd say, oh, I have my 81 over 2 squared plus my 81 root 3 over 2 squared, and you would end up still getting 81. Okay, that's the hardest part. We got this. All right, so we have r is 81, cosine plus I sine of 60 degrees. So if I'm taking the 4th root of that, I'm going to get 4 solutions, z1, z2, z3, and z4. So the 4th root of 81 is 3. 60 divided by 4 is 15. What number am I going to add to each of these? 90, right? So I'm taking my 360 divided by 4, I have 90 degrees. So each time I'm adding 90 degrees. So I'm going to have 3 cosine plus I sine, 105. 3 cosine plus I sine of 195. And 3 cosine plus I sine of another 9285. That's it. Okay, all of these before said leave your answer in trig or polar form. Look here. Simplify your solutions all the way down to this. So mean of me. All right, some of these are, well, yeah, I don't know if they're unit circle values. So if they're not unit circle values, we'll just use the decimal version of them. Now we could, I mean, if you really were like math-tastic, that's my new word, math-tastic. If you were like, I love math and I love everything trig, could you find cosine of 15 and sine of 15? Yeah, because you could do like the sum and difference formulas and all that. Oh, it would be so fun. But we'll not do that. Let's just use our calculator. So make sure your calculator, since we have degrees here, make sure we're in degree mode. And I want you to find cosine of 15. And then multiply by 3, right? So what I'm doing is 3 cosine of 15 for the first one. So I'm going to do 3 decimals. So I'm going to do 2.898 plus, and then I'm going to do 3 sine of 15 on the next one. So 0.776i. And then I'm going to do 3 cosine of 105 and 3 sine of 105 for the next part. So I get negative 0.776 plus 2.898 I. And then it continues. So you're going to do 3 cosine of 195 and 3 sine of 195. So I get negative 0.77. Oh, no, wait, that's not the first one, is it? It's the second one. I did them both. Okay, so I get negative 2.898 minus 0.776 I. And then the last one. Yeah, you think there's a little bit of a pattern there? You're right, there is a little bit of a pattern. Cosine of 285 times 3. Okay. So there's a pattern for that one because of the dividing, like the rotation of 90 degrees. So if you guys think about any answer, if I'm here and I go 90 degrees, I'm here, right? And then I'm here, and then I'm here. All of these are kind of like symmetric to each other. Does that make sense? So that's what's happening there. All right, so last little thing. So let's talk about these roots of unity again. So roots of unity, I think these are the easier ones because, I mean, it's just one. Like you have 1 as your first answer, so then you can just rotate from there. So suppose we have the equation z to the n is equal to 1. We know that there are n solutions to this. These are called the nth roots of unity. So the polar form of the number 1, right, that's 1 plus 0i, right? Think about where 1 plus 0i is. It's over here, right? So the polar form is 1 cis, what angle? 0. Yep. And so that's because we're at that point 1 comma 0. All right, so for each positive integer n, there's n distinct roots of unity. I'll give you again that formula, but hopefully you don't need that formula. You can just think about what the picture looks like, okay? So it says find the 8th roots of unity. So what are we saying? We're saying find where z to the 8th is equal to 1. So we want to take the 8th root of 1, okay? On the roots of unity, our first answer, surprise, is always 1. Do you guys see? So z1 is 1. Check. So if you want to write that as 1 cis 0, you can. Z2, Z3, Z4 are all going to follow from that. I don't know if I gave you guys much room. You don't have the extend page. I know you're so jealous. All right, so if I take my 360 degrees and I divide by 8, I get 45. So the next one's going to be 1 cis 45. Then I'm going to have 1 cis 90, 1 cis 135. And you just keep multiplying, like you keep adding 45 all the way down. Oops, I went too far. I missed one, didn't I? There we go. All right, I had to, mine got a little off. So let me circle them for you guys. Do you guys see those? All right, all of those are unit circle values. Do you guys see how 0, 45, 90, blah, blah, blah? So if you wanted to write these in that other form, you could. So for instance, this first one was just 1. This one is cosine of 45 is root 2 over 2. Sine of 45 is also root 2 over 2, like that. This next one's I, because you go 1 in the I direction. Does this make sense? This one is negative root 2 over 2, and then positive root 2 over 2, because we're in the second quadrant. Nick, you with me? Does this make sense? Do you guys see all these? So you could get all these. 180 is negative 1. This next one is negative and negative, so negative root 2 over 2 minus root 2 over 2i. this one's negative I, and this one's positive root 2 over 2 minus root 2 over 2I. That's the 8 solutions of x to the 8th or z to the 8th equals 1. Cool? 6th roots of unity, you guys want to try it on your own? So write them in the end, see if you can get them in this form, the a plus bi form. And this was the polar form. So try the 6th root of unity. All right, so let's say we wanted it in a plus bi form. So we know that we have the 6th roots of unity, right? So what we can do is we can think about the unit circle. And we can say, oh, my first answer is going to be here. And then I can take my 360 and I can divide into 6 pieces, right? So every 60 degrees, I'm going to have another answer. So if we continue going every 60 degrees, we get all of them, okay? Let's think about what those are, because we know those values from the unit circle. So Z1 is just 1, right? It's one of the answers for x to the 6th equals 1, or z to the 6th equals 1. All right, the second one is over 1/2 up root 3 over 2, right? Just remember how we've talked about, whoops, try to move that. So this is 1/2 root 3 over 2. So in a plus bi form, it's 1/2 plus root 3 over 2 I. The next one is negative 1/2 plus root 3 over 2 I, right? The next one is where pi is, right? So that's going to be negative 1. Then the next one is going to be negative 1/2 minus root 3 over 2I. And then the last one's going to be over 1/2 down root 3 over 2I. Okay? We jumped right to the answers. Easy? Could you do the 4th root, 8th root? I mean, you could do things like the 7th root. It's going to be a little weird, though. 7th root wouldn't be unit circle values, right? But like the 4th, the 6th, the 8th would be every 45 like we did. The 3rd, those would be unit circle values. Okay? All right. So let's stop there.